We all see it. AI is getting smarter, faster, more capable every single day. But here's the big question. Is it the same kind of smart as us? That's a question that feels more and more urgent. So today, we're going to dive into a really fascinating new paper that might just hold the answer. And it proposes a powerful new way to think about the difference between artificial intelligence and our own. Let's get right into it. I mean, AI can do stuff that feels like it's straight out of a sci-fi movie, right? It writes code, makes incredible art. It can crush us at the most complicated games. But even with all that, there's this nagging feeling that something's missing. It's like it can mimic intelligence, but is it really thinking? That's the mystery we're going to try and solve. So here's how we're going to break it all down. First, we'll frame the whole debate. Then we'll look at how your brain is basically a prediction machine. We'll connect that to why we do things in the real world, and then we'll contrast that with AI's very different approach. And finally, we're going to reveal the secret ingredient that might just be the key to the whole thing. All right, first up, is AI really intelligent? The conversation has totally shifted. It's not just about what an AI can do anymore. We're asking a much deeper question about the very nature of thought itself. A lot of folks, whether they're an AI or studying the human brain, are kind of landing on the same core idea. At its heart, intelligence is really all about the ability to predict. Being smart, fundamentally, is about making a good guess about what's going to happen next. Okay, but that right there, that creates a huge puzzle, doesn't it? If the AIs that power chatbots work by just predicting the next word in a sentence, and our brains work by predicting what we're about to see or feel, why do they seem so incredibly different? If they're both just prediction machines, where does this giant gap in real understanding come from? To answer that, we've got to look at how our brains play this prediction game. And this leads us to a really powerful theory in neuroscience. It's called the predictive processing framework. And the idea is simple, but it is profound. Your brain isn't just passively sitting there waiting for information to come in. No way. It is actively, constantly making its best guess about what's about to happen. Its main goal is to minimize surprise by making its predictions as accurate as possible. And this all happens in this nonstop loop. First, your brain predicts. It makes a guess. Then you sense what's actually happening in the world. And finally, you update. Your brain compares its guess to reality. Now, if there's a mismatch, what scientists call a prediction error, the brain has two choices. It can update its internal map of the world to be more accurate. Or, and this is the really critical part, it can act on the world to make reality match its prediction. And that idea of acting on the world, well, that leads us right into our next big point. Intelligence is for action. See, all this prediction stuff isn't just for fun, it's not some philosophical exercise. It has a very, very practical purpose. The paper we're digging into has a great name for this: adaptive control. Biological intelligence isn't about just sitting back and creating a perfect passive picture of the world. Nope, it's about using those predictions to actively control ourselves and our environment so that we can survive and thrive. It's intelligence for the sake of doing something. To really get this, think about a simple tick. It's got a tiny, tiny energy budget, so it can't just wander around looking for a meal. Instead, it waits, and it makes a single high-stakes bet, a prediction. The prediction is that the smell of a certain chemical means a warm-blooded mammal is walking by underneath. And based only on that prediction, it acts. It lets go, it drops. This isn't just some abstract pattern matching. This is a life-or-death prediction tied directly to action and survival. Okay, so you've got this image of the tick, right? This embodied, action-oriented intelligence. Now, let's flip the coin and look at AI's disembodied mind, because this is where we see the fundamental difference in how they learn. And man, when you put them side by side, the difference is just stark. We learn from being in the world, a world that's messy and always changing, and we're constrained by real things like physics and needing to find our next meal. AI learns from a giant static library of photos and text, a fixed snapshot of the world. It's like the difference between living a life and just reading the encyclopedia about it. And there's this perfect, almost funny example of this problem with an AI called AlexNet. It was trained to identify objects in photos, and it got really good at it. But when researchers dug in, they found something weird. It wasn't learning what a cat or a dog is. It was just learning to associate weird pixel patterns, like a certain kind of background blur, with a label. It learned about the pictures, not the world itself. It had no real grip on reality. Okay, so we've got the brain as this action hero predictor, and AI as this brilliant but clueless librarian. So, what's the secret sauce? What's the one thing we have that AI doesn't? Well, this brings us to the core idea of the whole paper, what they call the power of reconcretization. I know, it's a mouthful, right? Reconcretization. But the idea is actually super intuitive. Think of it like this. You have an abstract idea, like how to make a sandwich. Reconcretization is your ability to walk into a kitchen you have never seen before, with a weird toaster and the bread in a strange drawer, and still successfully make that sandwich. You use your body and your senses to adapt your general plan to the specific, concrete reality in front of you. You ground your idea in the real world. The New Caledonian Crow is an absolute genius at this. Its abstract goal is simple: hide my food so nobody steals it. So, in a forest, it knows exactly what to do. Use the trees, use the leaves, but take that same crow and put it in a totally new environment, like a riverbed. It doesn't just glitch out, it adapts. It reconcretizes its strategy, figuring out on the fly that it can now use the riverbank and some straw to do the exact same thing. And that right there is exactly what current AI systems struggle with. They are amazing at generalizing from their training data, at coming up with the abstract strategy. But because they don't have a body to interact with the messy, real world, they can't ground that abstract knowledge in a new, specific situation. They lose all those crucial little details that make the difference between a good plan and a successful action. So all of this, it all funnels down to one huge question. Does intelligence actually need a body? And what does this all mean for where AI is headed? So let's just recap. Here's the great divide we're talking about. For us, biological intelligence, having a body is absolutely essential. Our accuracy isn't judged by a data set, it's judged by survival. And our key skill is this amazing ability to reconcretize. For AI right now, embodiment is totally absent. Its accuracy is defined by its training data, and its key skill is this powerful but ultimately ungrounded form of abstraction. Which leaves us with this final thought. Maybe the path to true general artificial intelligence isn't about bigger data sets or more powerful computer chips. Maybe the next great leap for AI isn't into a bigger cloud, but into a physical body.